6C is discussing a specific type of distribution called normal distribution. So recall, distribution just means the shape of your data. Distribution is the shape. And a normal distribution is what we're going to explore today. It's a specific and very common type of shape. So the normal distribution is a bell-shaped curve. And so if you look to the right here at this image, it's called a bell-shaped because the curve that can be created by this looks sort of like a bell. So we call this normal or bell-shaped. Also notice that the mean is in my center. Remember, X bar represents the mean. Notice that I'm putting it in a position of the center of the data. Also notice that this distribution is symmetric about the mean. So if you see here, if I were to split this about the mean, about the center, everything is symmetrical about it. So that is another important quality to note about the normal distribution. Another rule that we want to go over that is specific to the normal distribution. It's called the empirical rule. The empirical rule is also referred to as the 68, 95, 99.7 rule. And so what that means, if you take a look at this image here, again, you have the mean in your center. And then if you go one standard deviation to the right and to the left, you are in a place where 68% of your data falls within that range. So I'll draw dashed lines here. 68% of my data will fall within one standard deviation. Again, a standard deviation, recall from last time, is on average how varied your data values are. A standard deviation is a single value. So if I go one standard deviation to the right of the mean and to the left of the mean, so I'm at these two dashed spaces, in between there, 68% of my data is within plus or minus one standard deviation. When you go out plus or minus two standard deviations, 95% of your data falls in that range. And if you go out further, plus or minus 3 standard deviations, we approximate that 99.7% of our data falls within that range. Again, this is called empirical rule or 68, 95, 99.7 rule, and it just discusses only for normal distributions, again, bell-shaped curves, how much data, the percentage of data that falls within 1, 2, or 3 standard deviations from the mean. So let's take a look at applying the empirical rule. It says, using the empirical rule with remember, this means the mean, and S refers to the standard deviation. So if our mean is 50 and the standard deviation is 10, what percent is between 50 and 60? So let's look at that. If we're using empirical rule, we know that we're dealing with a bell-shaped curve. They give us our mean, so I'm putting that in the center. The mean is 50. And just underneath, I'm making a note of the standard deviation. It's 10. They want to know what percent is between 50 and 60. Well, let's think about this. 50 is right here. 60 would mean I would have to do 50 plus another 10. That's one standard deviation to the right. I got this by doing the mean plus standard deviation of 10. That gives me 60. I want this space. Now, I also know if I go one standard deviation to the left, So let me do that in a different color. The value I'm getting is the mean minus the standard deviation. And I'm subtracting the standard deviation this time because I'm going to the left. This value would be 50 minus 10, which is 40. And what the empirical rule says is if you go one standard deviation above and below the mean, it says 68% of my data falls in that range. But remember, we only want this piece that I shaded, which is exactly half of this whole thing. The 68%, I'm going to try to highlight it. The 68% takes into account this piece right here. I just want that half. So to find that, I'm going to do 68% divided by 2, and that's 34%. That's the percent between 50 and 60. Let's look at another example. What percent is above 60? So let's draw this out one more time. We have a normal distribution. The mean is 50, and the standard deviation is 10. What percent is above 60? So remember, we just found if we go one standard deviation to the right and to the left, that means I did the mean minus the standard deviation here and the mean plus the standard deviation. This got me 60. And we said this was 50 minus 10, which is 40. We said 68% of our data falls in that space within plus or minus 1 standard deviation. Now I'm interested in what percent is above 60. Above 60 means I'm interested in this now. Well, again, let's take advantage of the fact that the whole curve must add up or total to 100, right? I'm dealing with percents. Also, let's note that this is symmetrical. So 100 minus 68% would give me 32%, meaning 32% is in the tails. When I say tails, I'm referring to this and this. These are my tails. This tail plus this tail, the left tail and the right tail, add up to 32%. But if I only want the tail that's shaded in red there, because this is symmetrical, I can just do 32% divided by 2. Cut it in half, and that gives me 16%. This is 16%. So is this. And if you add 16, 68, and 16, you would get 100. Let's look at this next example. What percent is below 30? So let's draw our normal distribution again. We know our mean is in the center, it's 50, and our standard deviation is 10. Now I'm interested in going below 30. So I need to figure out how many standard deviations do I have to go to get to 30. If I go one standard deviation to the left, because 30 is to the left of 50, I would have 50 minus 10, which is 40. If I go 2 standard deviations to the left, then I would subtract 10 again, and I would get 30 this time. Or one way I could look at this is the mean minus, because I'm to the left, 2 times the standard deviation. If I calculate that, that's 50 minus 2 times 10, which is 50 minus 20, or 30. So I had to go 2 standard deviations. I'm in the center, and then I go 1 standard deviation away, which means 50 minus 10, that's 40. And if I subtract another 10, now I'm 2 standard deviations away, and that gets me 30. So I went to the left 2 standard deviations, and the empirical rule says if you go to the right 2 standard deviations, 95% of my data falls in that range. This value would be X bar plus 2 times the standard deviation. So the mean plus 2 times the standard deviation, which would be 70. We're interested in what percent is below 30. I want this piece. We know that the whole curve has to add up to 100, right? So that means if I do 100 minus 95%, I have 5%, but that 5% must be split between the two tails. So 5% divided by 2 is 2.5%, meaning this is 2.5%, and so is this piece. And the whole total adds up to 100%. Let's look at the next example. Normal exam. For each of the following exercises, consider a psychology exam on which the scores were normally distributed with a mean of 67 and a standard deviation of 8. So let's draw that out first. Normally distributed, so bell-shaped, with a mean of 67 and a standard deviation of 8. A failing grade on the exam was anything 2 or more standard deviations below the mean. What was the cutoff for a failing score? So, if a failing score is 2 or more standard deviations below the mean, let's calculate what that would be. Its position would be to the left because it's below the mean or lower than the mean. And I need to go 2 standard deviations to the left, which means I take the mean and I subtract 2 times the standard deviation. So that value would be 67 minus 2 times 8. And if I do that, I should get 51. So for the first question, it is, what was the cutoff for a failing grade? Well, the cutoff would be 51 or lower. Failing would be 51 or lower. Now we went 2 standard deviations to the left, right? So if we also went 2 standard deviations to the right, that would be the mean plus 2 times the standard deviation. That's 67 plus 2 times 8. So that would be 83. Empirical rule says that if you go 2 standard deviations to the right and to the left of the mean, we know 95% of our data falls in that range. Look at what the second part of this question asks. Approximately what percentage of the students failed? We said failed is if you got 51 or lower. So we're looking at what percentage falls here in that shaded piece. Again, we know the whole curve must add up to 100. So 100 minus 95 means there's 5% left, but 5% is split between the two tails. So I'll do 5% divided by 2, and that's 2.5%. This would be 2.5%, and so would this. But we're interested in this piece. So approximately 2.5% of the students failed. Now it says if 200 students took the exam, approximately how many scored above 59? So let's go ahead and draw this one more time. I'm dealing with a normal distribution. We were told earlier that the mean was 67 and the standard deviation was 8. But now we're interested in how many students scored above a 59. So 59 is going to be somewhere to the left of the mean, but I need to figure out how far away it is, how many standard deviations away it is. So if I go 1 standard deviation to the left of the mean, I would be doing the mean minus S, minus 1 standard deviation, which is 67 minus 8, and that is 59. That's me going 1 standard deviation to the left. We want how many students scored above 59. So I'm interested in this. Anything above 59, that whole piece. Now, how can I figure out the percentage there? Well, I went 1 standard deviation to the left. If I go 1 standard deviation to the right, that's the mean plus a standard deviation. And that would be 67 plus 8, which is 75. The empirical rule says when you go plus or minus 1 standard deviation, 68% of your data falls in that range from here to here. So I have some of this shaded piece, but I need this right tail. Remember the pieces that in these 2 tails plus this middle piece have to add up to 100. So if I do 100 minus 68%, that's 32%. 32% in both tails. If you add up both tails, they add up to 32%. But I only want this right tail. So let's do 32 divided by 2. That's 16%, which means this is 16%. So this shaded piece is 68 plus 16, which is 84%. Figure out how many students, if there are a total of 200 students, we would do what is 84% of 200, which is 0.84 times 200. That gives me 168 students. You have to pay attention to the question here. They didn't ask for what percentage. They asked how many students scored above a 59. So I first had to figure out what's the percentage of students that scored above 59, which was 84%. And then I did 84% of 200. Remember, of is a key word for us that means multiplication. And when we were dealing with that unit about percents, remember, we always converted percents to decimals in order to do our math. Okay, 2 more things I want to go over as far as concepts in this class is z-scores and something called a percentile. So let's talk about z-scores. What a z-score is it tells you the number of standard deviations a data value is above or below the mean. So every data value in your data set can be converted to a z-score. And a z-score can be negative or positive. It depends on the location of the data value. If it is to the right of the mean, then your z-score is positive. If your data value is to the left of the mean, then your z-score is negative. And again, a z-score just tells you how many standard deviations away the value is from the mean. This is the formula for the z-score. I wrote it in words and then symbolically here. And I'll mostly refer to symbolically. It is your data value, that's what X represents, minus X bar. X with the line on top means the mean, and you divide it by the standard deviation S. And then the other thing I want to talk about is percentiles. Percentiles are very similar in concept to quartiles. It talks about your position in a data set. So remember, quartiles separated your data into 4 pieces, and therefore there were 3 quartiles. With percentiles, we think of percents. And so percents are out of 100. So what a percentile does is, let's say you have a data set, it separates your data into 100 pieces. And in order to separate it into 100 pieces, I would have 99 percentiles. So you go from 1 percentile up to 99. The percentile is the percentage of all data values in a data set that are less than or equal to it. So for example, if I was in the 70th percentile, we do see percentiles often. Let's say you're taking a standardized test like a SAT. You'd get your results, and your results would also indicate what percentile you were in. So if you were, for example, in the 70th percentile, that means your position right here is located in between the bottom 70% and the top 30%. That is what the 70th percentile means. It means you did better than 70% of people that took the SAT that day, and 30% of people did better than you. Okay. Let's look at example 3. It says, use the definition of standard score, which is called the z-score, to answer these questions. Complete the statement z equals for each data value. It says a data value 0.3 standard deviations above the mean. So remember what a z-score means. A z-score tells you how many standard deviations away from the mean a data value is. So even if we don't know the data value, if it says it is 0.3 standard deviations above the mean, we can say our z-score is 0.3, and it's positive because we are above the mean. We are to the right of the mean. A data value 2.7 standard deviations above the mean. The z-score is how many standard deviations away you are. We're 2.7 standard deviations away. We are also above the mean, meaning to the right of the mean. So our z-score would be positive. A data value 1.2 standard deviations below the mean. So the z-score is 1.2, but this time I'm below the mean, meaning I would be to the left of the mean. So this would be a negative z-score now. The positive or negative just indicates where you are. Are you to the right of the mean, or are you to the left of the mean? Are you above the mean, or are you below the mean? Example 4, SAT scores. SAT exams are designed so that their scores are normally distributed with a mean of 500 and a standard deviation of 100. Complete the statement z equals a score of 443. So that score is a X. That's an individual data value. And what we're being asked to find is, what is the z-score? for this data value. Remember the z-score formula. It is your data value minus the mean divided by the standard deviation. Well, our data value is 443. The mean, they give that to you in the problem. And the standard deviation, they also give you that. That's 10. Oh, I'm sorry, 100. And so if we do that on the calculator, we'd get negative 57 over 100. And this, we always want to round our z-scores to 2 decimal places. And I'll show you why in a second. We're going to look at something called the z-table. And that z-table, all the z-scores are rounded to 2 decimal places. So when you divide negative 57 by 100, you should get negative 0.57. And again, we should expect this z-score to be negative because if our center, let's say I wanted to draw this out. If my mean in the center is 500, 443 is somewhere to the left of that. If I wanted to make that into a z-score, if the value is to the left or below the mean, it is going to be negative. Same with part B here. 287 is somewhere to the left of the mean. So I should expect my z-score to be negative. It would be your data value, which is 287 in this case, minus the mean divided by the standard deviation. In the numerator, I would get negative 213 divided by 100. And when you divide that, you should get negative 2.13. Let's look at standard scores, which again, standard scores just means z-scores, and percentiles. So we're going to use this table to find the percentile of the following data values. A data value 0.3 standard deviations above the mean. So when I do this, I'm going to show you this table. If I'm 0.3 standard deviations above the mean, that means I have a z-score of positive 0.3. Now in our notes, right before I start section 6C, I have a table here. So here's section 6C. We have a table here. This is our z-table when z is positive. And we also have another table when z is negative. So since our z-score was 0.3, I'm going to go to the positive table and I want to show you how you read this table. On the perimeter here and here, on the perimeter here, we have z-scores. And the way you read this is like this. Let's say I wanted to find 0.3. It is look here and find 0.3. And then on this row, you have the hundredths place. Well, 0.3 is the same thing as 0.30. And then I look at where it matches up. This row and this column would match up right where I boxed in, 0.6179. I call these values here, that's the body of your table. And these are areas to the left of the z-score. So for us, our answer is 0.6179, but we want to make it a percent. So to make this a percent, I'm going to write here what we had. 0.6179, that was our area. That's what the table said. I can make that a percent by moving it 2 places to the right, moving the decimal point. So what that means is we're in the 61.79 percentile. So what does that mean? That means 61.79% of data values are lower than this value. Look at the next one, a data value 2.7 standard deviations above the mean. Well, that would mean a z-score of 2.7, and it would be positive because we are above the mean or to the right of the mean. So I'm going to go to my table, my z-table, and find the percentile with a z-score of positive 2.7. So we're on the positive z-table, and let me erase some of these marks here. Make sure it says positive. If my z-score is 2.7, at z column, we're going to go to 2.7 to the 0.00 column as well. So that matches up right here. This would be 0.9965. So when I go here, 0.9965, if I were to make that a percent, that is 99.65 percentile. It separates the bottom 99.65% from the top. For part C, a data value 1.2 standard deviations below the mean. Well, if we're below the mean, that means my z-score would be a negative 1.2. So let's look at the negative z-table. So here we're at the negative z-table, and look at negative 1.2. So I'm on this row, and I'm in the 0.00 column, negative 1.2, and that's 0.1151. That is my area. For us, that would mean our percent, but I need to make it a percent. And to do that, I'm moving the decimal point 2 places to the right, which makes this 11.51 percentile. Look at another example. Let's say I said negative 1.22. That was my z-score. So we would go to the negative 1.2 row. And I apologize, guys, I have to move so many times. Negative 1.22. So I'd look at the negative 1.2 row, and you see this 2 is in the hundredths place. So look at this. Let me do this. Let me erase the rest of these. Look at right here at the 0.02, because 1.2 plus 0.02 gives me 1.22. And so that would be this value, 0.112. Let's practice with another one. Let's say I score of 3.43 negative. Well, here's negative 3.4, and then the 0.03 column makes it 0.0003, which as a percent, 0.03%. Let's look at the next example. And so this is about just 10K time. So we're racing, and it says, suppose you organized a 10-kilometer race in which times were normally distributed. So as soon as I see that it's normally distributed, I'm drawing my bell-shaped curve. with a mean of 58 and a standard deviation of 8. So we're talking about 58 minutes and a standard deviation of 8 minutes. What percentage of runners finished under 52 minutes? So if 58 is in my center, 52 is to the left. Let's say it's somewhere here. And I'm going to say this is X. X is 52. That's my data value. I'm interested in what percentage of runners finished under 52 minutes, meaning below 52 minutes. So I'm interested in this. Now, I'm seeing that 52 is not exactly one standard deviation below the mean. And how do I know that? If I did 58 minus 8, I would get 50, which would be exactly one standard deviation. But I'm not. I need to look at 52 and below. So I'm going to have to turn this data value into a z-score. And so let's practice doing that. Remember, the formula is the data value minus the mean divided by the standard deviation. So for us, that would be 52 minus 58 divided by 8. And if you subtract and divide by 8, you should get negative 0.75. So what we've just done is we've turned this value, 52, into a z-score. What it means is 52 is not quite one standard deviation away. It's like 3/4 or 0.75 standard deviations away from the mean. Now, how will I get this shaded piece? I'm going to look at my z-table. But I'm going to look at the negative z-table because my z-score is negative. That's what determines which table you look at. So if we look at our negative z-table, so I want negative 0.75. So we're at the negative 0.7 row. And let's go to the 0.05 column, which is over here. And so if I follow that down, I get 0.2266. I also want to make a note of this. These areas in the body of your table, they say in this table that they are areas or probabilities. They are to the left of Z. So take a look at this image right here. I have a bell-shaped curve. If this is my z-score, what I just found, 0.2266, that's this piece. That would be 0.2266. From the left, that's what that's emphasizing there. So let's go back to our problem. I'm looking for that piece to the left. So this would be my answer, 0.2266. But we want to make it a percentage. So let's move the decimal 2 places to the right. And that would be 22.66%. Now it's asking us what percentage of runners took longer than 70 minutes to finish. So I'm going to draw this normal distribution again. My mean is 58 and my standard deviation is 8. Now I'm interested in longer than 70 minutes. Well, I know 70 is going to be somewhere here to the right, above 58. How do I determine how many standard deviations that is? Well, let's do, once again, the z-score, the data value minus the mean divided by the standard deviation. That's 70 minus 58 divided by 8. If I subtract 70 minus 58, that's 12. 12 divided by 8 is 1.5. So this is a positive 1.5. So I'm going to look at my positive z table now and look for 1.5. So you see I'm on the positive. And here's the 1.5 row, and I'm going to match it up with the 0.00 column, and that gives me 0.9332. Remember, these are all to the left. So 0.9332 is this piece right here. But what am I looking for? What percentage of runners took longer than 70 minutes? So I'm looking for this piece, more than. Let's make 0.9332 a percent. That would be 93.32%. And if I know this whole curve has to add up to 100%, to get this piece, I'll just do 100 minus 93.32%. And if I do that, I'll get 6.68%. That is that piece. We were able to do this because we knew under the whole curve, it must add up to 100. So if I have this piece to the left, take 100 minus that piece, and I'll get the shaded region I need. Look at the last example. About what was the time of a runner who finished faster than all but 1% of all finishers? So we're dealing with the same normal distribution. My mean is 58, and my standard deviation is 8. I want to be in a position where I finish faster than all but 1% of the finishers. Think about what we're looking at. We're looking at 58 minutes, right? In the center, in my middle, the average runner took 58 minutes. If I finished faster than most people, I should be somewhere over here, less than 58. And I only want 1% of people to finish ahead of me. So what I'm trying to figure out is this. What time am I at where only 1% of people finish before me? So that is how you determine the location. If you're finishing faster, that means you are less than 58 minutes, which is the average. So I should be somewhere way to the left. Now, because I can't figure out X, they don't give it to me, and that's what I'm looking for. What was the time? I do have this piece that's to the left. I also know that the z-score should be negative. And the reason why I know that is because we're to the left of the mean. We're below the mean. So what I'm going to do is I'm going to work backwards. I do have an area that's from the left. This as a decimal would be 0.01. So I'm going to look, so make sure you're on the negative. And instead of looking at score, because I don't have it, it says the body of your table are the areas to the left. So let's look up 0.01. As I'm looking here, I'm kind of focusing on this negative 2.3 row, and I'm seeing values that are close to 0.01, but I'm not seeing exactly 0.01. And if that's the case, I'm stuck between these two values. And so the rule is pick the value that is closest to 0.01. The closest to 0.01 would be this value. And so now I can look up, well, what's the z-score for that? It would be negative 2.33. So what I'll do is I'll say this, I don't know the exact value of it yet, but I know the z-score is negative 2.33. Now we can take advantage of the z-score formula. Remember, this is the z-score formula. I have practically everything except x. I have my z-score. I don't know x, but I have my mean, that's 58. And I have my standard deviation, that's 8. So now what I'm going to do is I'm going to cross multiply. I can make this a fraction by saying it's over 1. And cross multiply means multiply diagonally. 1 times x minus 58 is just x minus 58. And then multiply diagonally in the other direction. Negative 2.33 times 8, that's negative 18.4. And now I want to solve for x. Add 58, you should get 39.6. So that is your value. That is the time where you finished faster than 1% of the finishers.